Oftentimes when we are conducting some type of study, we know what our margin of error would like to be, or at least we want to figure out how we can minimize our margin of error so that we can give a narrow interval for the true estimate of the mean. There are three ways to do this just looking at the formula. So if you notice, because z star, we can kind of think of it as being like in the numerator along with sigma. If either of these get smaller, then the entire margin of error will get smaller. So that's our first two bullet points here. Now, practically speaking, we don't have much control over sigma. And we do have control over z star, but think about what that means for our confidence interval. If z star gets smaller, meaning it gets closer to 0, then the area is getting smaller, meaning our confidence level is smaller. So that's not always an ideal way to decrease our margin of error. Again, we don't always have control over sigma, so our next best bet is to look at n. If n gets larger, since it's on the denominator of our formula, then our margin of error will decrease. While each of these three changes will make our margin of error smaller, this is the most ideal of the three and the one that's easiest for us to control. So it might be that we're looking to decrease our margin of error, or in another instance, we might have an idea of exactly what we want our margin of error to be. And example 10.7 is going to look at how we can determine a sample size to ensure a specific margin of error. In example 10.7, this is talking about how many monkeys we need to survey. We have a standard deviation given to us. We know that we want 95% confidence. And it says that we would like to estimate within 1 milligram per deciliter of blood. So the desired margin of error goes here. The margin of error formula is over here, so we have our z star times sigma over root n. We put in the information that we have. We know that our standard deviation, again, is 5. We know that because we want 95% confidence, our z star value is 1.96. And then with our margin of error over here on the other side, then we just need to solve that inequality. What I want you to notice, what's super, super important here, is that regardless of typical rounding rules, we always round up to the next whole number. So look at the inequality. It says n is greater than or equal to 96.4. Since we can't survey a decimal number of monkeys, we have to take n to equal 97. 96 won't quite give us the margin of error small enough to be 1. Lastly, I just want to reiterate a few things that we've already mentioned in class. The data has to come from a simple random sample of our population of interest. If we have badly produced data, especially if it has a large bias, no calculation can correct for that. So we can't alter our confidence level if the data is bad in the first place. We just shouldn't be running the calculations regardless. Outliers can really distort the results. Remember that right now we're focusing on means, and since means are strongly influenced by outliers, it's not good if we look at a data set and we have some outliers present. I also want you to be aware that even if outliers aren't present, the shape does matter of the distribution, so strong skewness is also something we want to be leery of. Hopefully, if a distribution is not normal, then we have a sample size of at least 30, and that way the central limit theorem will ensure our calculations are fairly accurate. And lastly, if we don't have the population standard deviation, we're going to use a different distribution of values, and this is to come in the next class.